Hi everyone. This video is the solution for example 1 to example 4 on the topic of statically determinate frames. The main idea of this topic is to make you understand that there are different ways to solve this type of problems, and it's your decision to figure out which one is the best and figure out different ways when the one that you try first doesn't work. So when you solve this type of structures in the first year, you learn first how to get the reactions, then you learn how to calculate the shear force diagram, and then with the shear force diagram you can take the area and get the bending moment diagram, and then finally with the bending moment diagram you can get the deflected shape. Now, what's interesting about these problems is that there is no particular reason why you need to solve the reactions first and then the shear force diagram and then the bending moment diagram and then the deflected shape. You could very well start with the bending moment diagram and connect it to the deflected shape, or use the information from the reactions and the bending moment diagram to get your shear force diagram. So what I'm trying to say in these examples is that everything is interconnected. And solving this type of structures basically means that you can start whatever you want, and then you can use the other concept to build your solution and make sure everything is correct. So let's look, for example, into example 1, and let's solve it using the classic way of starting with the reactions. So in this case, we know we have a horizontal load of 20, so the reaction at C needs to be 20 as well. And if we have a load of 8 times 4, 32, that means we have a reaction of 32 here. In terms of moments, both of these moments are clockwise, so that means we need a counterclockwise reaction, and then the total force is 20 times 3, 60, and then 32 times 2, 64, so that's 124. So you could get the reactions straight away. So with these reactions, you could get the shear force diagram. So in this case, we could see that the load of 20 here will cause the shear force in this bar to be 20, and then the load of 20 at B will close it down. And then the shear force in BA starts with this load of 32 that pushes it up over there, and then the UDL will close it to 0 because the area of that load is also 32. So this should give you the shear force. Now, if we go to the bending moment diagram from this case, we know that the bending moment diagram at A, so at the tip of the cantilever, is equal to 0. So we could take, for example, this area, which is 32 times 4 divided by 2, that gives me 64. We could get the moment there at that point. So, and we know, since this is a UDL, we get a parabolic distribution for your moments. Now, that's 64, so we know that this transfers outside, and this gives me 64 as well. And the reason here, guys, is if you zoom in on that node, okay, if we try to do a zoom in there, what we see is the 64 that causes tension on the top, so it looks like that, needs to be balanced by another 64 that will cause tension on the left side, okay? So that's why we know moments that come from the top side get transferred to the left in this case, and then when you solve a case where the 90-degree angle is on the other side, we can do this again. But the mnemonic here is know that moments that are outside of the structure stay outside, moments that are inside stay inside. Now, the only thing we have to do is to figure out the moment at the end. So we could say straight away from the reaction that the moment is going to be 124. So we know that's 124 here. And again, no UDL here, so we can connect it with a straight line. Another thing we know is if it goes from 64 to 124, we know that that area here of 60, which is 20 times 3, is the reason why we can go from 64 to 124. Okay, so this is my bending moment diagram, and then finally we can get the deflected shape. The only thing we need to know for the deflected shape is that the bending moment diagram is always drawn in the side of tension. So we know that because of the bending moment diagram that we see here on the left, the tension is going to be on the left side on the column and then on the top side of the beam. This information, with the fact that we know there's a fixed support here, we can guess that the deflection is going to look like this and then bend that way. And here we need our 90-degree angle to stay 90 degrees, and the beam will bend more or less like that. And this is obviously exaggerated, but tension on the top and then tension on the left side. Now, what's interesting about this problem is that this deflected shape could very well be obtained straight away from the beginning. Just by looking at this structure and knowing that this is a fixed support, we can guess that most likely this one is going to be the deflected shape. So we didn't have to go through all these steps to get that this should be the way the structure is going to deform. So in this next problem, for example, we can start with the deflection. We could say, okay, this is a fixed support here, so this can't rotate, can't move, but then there's a load of 10 pushing this point to the right, there's a load of 60 pushing this point down, so most likely this will bend as well, like that. So straight away, when we go to our bending moment diagram, we can see that we're going to have tension on the left side and we're going to get tension on the top side. So now we could try to calculate the moments in a different way. For example, what should be the moment here at B because of the load of 60? Then we can say that the moment here at that point is 240 because that's 60 times 4. Then we know that that just transfers outside, so this moment here is also 240. And then if we want to know the moment here at C, that's just 60 times 4, 240, but then we add 10 times 3, so we get 270. And this is it. We can get the bending moment straight away just by looking at the forces and the geometry and by looking at the deflection. Now, if you want to do the shear force diagram, you can see that the shear force diagram, the same way we could calculate the bending moment diagram from the area of the shear force, we can also calculate the shear force as the slope of the bending moment diagram. So for example here, we can see that the slope of this line is 30 divided by 3, so it's the difference divided by the length, so the slope here is 10. And the slope in this one is 240 divided by 4, so the slope here is 60. So we could say that the shear force, since the shear force is the slope of the bending moment, there is 60 and here is 10. And now let's see if this will make sense with the reactions. If you guys check the reactions now at the end, the horizontal reaction will be 10 to the left, which matches well with this 10 here for the shear force. And we know that the vertical one is 60, which then is the shear force for your beam BA. So this is all looking good. Let's check the next problem. So similar problem here. We do have a moment of 40 at A, which should make the bar do something like that. So we should get tension on the top. And on top of that, we can see the load of 15 pushing the point B to the right. So most likely we'll have tension on the left. So with this information, we can start calculating our bending moment diagram, knowing that this moment of 40 is indeed a negative moment, will make our beam SAD. So this will be constant from A all the way to B. And then this will get transferred here to 40, which then means at C, that's the only moment we need to calculate, that's 40 clockwise plus 15 times 3 also clockwise. So this reaction here should be 85. And here we can see that reaction indeed gives me tension on the left side. So this all adds up. That's 85, and this is a straight line. If you guys want to know the shear force, again, this slope is 45 divided by 3, so we can see that this slope is 15, which then means the shear force should look more or less like this. 15 on the column, and then 0 on the beam. And why 0? Because the slope here on this line is 0. We have a constant moment of 40. And now, if we check the reactions, for that shear force to be 0 in the beam, that means this reaction here needs to be 0, because it's this reaction that will give you the shear force there at B. And this makes sense because we don't have any vertical load, so that makes sense for the shear force to be 0 over there. So this is looking good. We have one more problem to finish. Very similar. Also looks like the deflection is going to be something like that. We have indeed a load of 30 that will bend bar BA as a sad bar. So by the way, this should be a 90-degree angle, so this is not very good drawing, but works for now. So let's go and get our bending moment diagram in this case, figuring out that the load of 30 will cause at point B a moment of 120, tension on the top, and then straight line here. And then this 120, I know there's a load of 30 there, but imagine that it's not, we would get the 120 to just transfer this way. So let's just zoom in this node again and have a look at what's going on there. We do have the 120 doing tension on the top side here, and usually this transfers 120 to this side so that we have tension on the left side. So this is an equilibrium. We have a clockwise moment of 120, we have a counterclockwise moment of 120, so that's pretty good. But now in the node itself, on the node, we have a moment of 30, which then means now this is not in equilibrium. So if we have 120 coming from this side and 30, that means this moment here is not 120, should be 90, okay? So we can get rid of this 120 and substitute it with a 90, okay? Now, the moment at C, if we think about the moment at C now, we still have 30 times 4 clockwise, we have the 30 counterclockwise, so that means the reaction also needs to be 90 counterclockwise. So with all this information, we can guarantee that this moment here is also 90, tension on the left side, and this will be constant. So now, for my shear force, we can see that the moment on the column is constant, right? The moment on the column is constant, so the slope here is 0. Again, slope 0, so the shear force must be 0. The slope in this one here is 120 divided by 4, so should be 30. And that should give me the value of the shear force over there. Okay, let's just confirm this with the reactions. The vertical reaction here is indeed 30. And then the horizontal reaction is indeed 0 because we don't have any horizontal load. So this one here causes or doesn't cause a shear force in BC. And then the load of 30 causes a shear force in AB. And this all makes sense. The deflection, the bending moment diagram, the shear force, and the reactions are all interconnected. Okay, so I hope you enjoyed this video. This is the lesson that I want you guys to get from this. All these 4 concepts are connected. It doesn't matter which one you start with the one that seems the most obvious. And with time, you're going to start training your muscle on understanding how to solve these structures faster. And when you fail, you always can check other concepts to try to paint the picture in a little bit better. So these ones are quite simple problems. We're going to do a couple more in the next videos. But for now, I'm happy with what we covered. Thank you for watching and have a nice day.